Yeah, great. Super duper excited to be here. Thanks for inviting us. Really excited to tell you all about CubeSigner, which is our sort of the hardware-backed key management solution that we've designed. Yeah, I really want this to be sort of a nerdy technical thing, which usually isn't kind of the habit for me. So we'll get there. But first, I really want to just really briefly introduce the rest of the Cubist team because I couldn't be here without them. So Anne, our COO, has about a decade's experience in fintech. She has a lot of expertise in fraud prevention, so she's been super helpful in terms of telling us how to, think about, catching cheaters and building policies that sort of heuristically catch bad behavior. Dayan is our chief scientist. He's a professor at UC San Diego, where he builds real-world secure systems, and his focus is really on sort of designing systems that can safely run and interact with untrusted code. So usually what that means is something like the sandboxing mechanism that Firefox uses to protect the browser from third-party libraries, other kinds of cool and interesting stuff like that. Fraser, our CTO, is a professor at Carnegie Mellon. She focuses on software correctness, so things like automatically finding high-severity bugs in browsers and operating systems, and also formally verifying parts of extremely complex systems, things like Firefox's JavaScript JIT and the Crane-Lift WASM compiler, which is used in production by Fastly right now. Unfortunately, I can only fit the founding engineers on the slide. I wish I had room for everyone because I'd love to brag about all of them because they're all super awesome. We have a great engineering team. They're industry and academic experts in things like DevOps and security and formal verification. So they're absolutely a pleasure to work with. And finally, I'm the CEO, and also I'm a professor at Carnegie Mellon. My research is on applied cryptography and zero knowledge proofs. I've gotten to work on all kinds of cool and fun and weird things like decentralized auctions and anonymous airdrops and trustless bridges. But validators and validating is like especially close to my heart because I helped to design and standardize the signature scheme that's used by the Ethereum beacon chain. So when we got started thinking about key management for staking applications and like sort of making validators safer, the question that we started from was kind of like, how could you be sure that your validator was safe from kind of all the bad stuff that could happen? Whether that's like attackers or operational threats, like messed up infrastructure or accidental slashing. And I should say, to be clear, I mean like safety here in the sense of it does not do the bad thing. Uptime, of course, is also extremely important, but it's kind of a different quality of problem. So in terms of this question, like how do you make a really safe validator? It seems like what you want, like notionally, is to make sure that your keys can only sign the right messages, right? Because somehow, like if you focus on the keys, then that's like focusing on the validator's interface to the world. That's the way that they interact with the world. Whether you're depositing or testing or exiting, everything happens by signing a message and sending it somewhere. And so even though it sounds like slightly magical to just wish for a key that could only sign the right message, that actually does kind of simplify the problem, because what it means is you can immediately rule out this huge class of misbehaviors that would result from things like buggy validator clients or your infrastructure going weird or whatever. Because if the key won't sign a bad message, then like even if everything else goes wrong and somebody tells it, please sign this bad message for me, it'll say, no, I will not. It's a bad message, right? So somehow it does like kind of reduce the problem to a little bit of a kernel, and then we can kind of attack that problem. So how do you attack that problem? Well, I mean, the first answer is it's a hard problem to attack, right? And y'all know better than anyone else that like attacking this problem, but like managing keys and for staking at scale is like even more demanding than being a solo staker, right? Like you've got to handle much more infrastructure and you've got much more stuff to worry about. And that was the kind of setting in which we started to think about CubeSigner. Like, how do you meet the demands of like huge, a huge validator operator? So specifically, we kind of focused on what we think of as the 5 most important constraints. So obviously, you need performance and reliability. You can't be late with your signing. You can't be, going down all the time. Like obviously, those are things that you totally need. You also need disaster recovery and, all of this sort of thing. You want global slashing protection. You want to make sure that basically, no matter what happens, you will never sign a message that gets you slashed. right? You want protection against insider threats and attackers. If you're a big operator, potentially you've got, a bunch of people who have to be able to maintain the machines, who have to be able to have access to them in order to, operate the infrastructure. And you want to make sure that none of those people can, do evil things as a result, right? This is also protecting against mistakes, right? So even better. You want to have security on the deposit and exit or withdrawal workflows too, right? You want to make sure that people can't steal your money and stake it for themselves or front run your keys. And you want to make sure that migration is easy and secure. And here I mean like migration to and from like the CubeSigner management, but I mean migration from one validator to another. Like generally, maintenance should be like an easy thing. Okay, so I don't want to keep you in suspense. So I'll tell you right now, CubeSigner meets these goals, in our view, and basically. So I'll give you a couple numbers. So we're in production right now. We can easily scale to hundreds of thousands of keys with like 5 nines of reliability. Our latency runs about 125 milliseconds, which means empirically that attestations happen on time. And okay, so I've gotten the top line numbers out of the way. That means I can like nerd out about some like lower level technical details of how we designed CubeSigner to kind of meet these requirements. So if we look at the sort of high level architecture of CubeSigner, it's kind of 3 big pieces. First is a REST API that lets you sort of generate and manage and use keys. And the idea there is really just make it integrate cleanly with existing stuff. There's a policy engine that lets you control what each key can do at fine grain. So this kind of goes back to that idea of making sure the keys only sign the right things. And then there's a virtual HSM that we build by sealing together a hardware-backed enclave and a hardware security module. So the overarching design principle here is keys are always protected by secure hardware during their entire life cycle, whether they're being used for something like signing or whether they're being generated or like no matter what, they're always inside of the secure hardware. One exception to that, which we'll get to later, is export and key recovery. Those are important too, but basically the thing to keep in mind here is you never access the raw key. Instead, you use a revocable token that lets you manage keys and create signatures without revealing the secret. Okay, so right now all of this is built on top of AWS, which is part of why we can make it globally distributed and highly reliable and extremely scalable. But that said, our roadmap includes other clouds and eventually getting down to bare metal too. So now I'm going to go into each of these pieces in just a little more detail. So. The REST API, as I mentioned, really the idea here is to focus on security and ease of integration. So how do you make integration as easy as possible? Well, you just make it work with existing validator clients, right? So there's already a standard for this, right? The sort of the Web3 signer interface that a lot of clients already work with. And so what we did was we built a sort of Web3 signer compatible sidecar that runs alongside the validator client and handles all the sort of low-level details of authenticating to the API and automatically retrying if your network is weird or whatever that might be. For security, we also have multi-factor authentication and multi-approval. So that means that you can require multiple people to sign off for particularly sensitive actions. And we also thought really carefully about sort of the entire life cycle of a validator, from pre-generating keys to staking to validating to unstaking. And the API separates the privileges for these actions. So for example, that means that your validator's credentials cannot be used to initiate a deposit. And the API also processes protocol messages, not raw hashes, which means that it sort of ties nicely into the next piece, which is the policy engine. So the policy engine analyzes signing requests for compliance with policies that you can set per key and per credential. Now, maybe the most important policy, which is always enforced, is that the validator is just not allowed to sign any message that would result in slashing. So this is backed by a globally distributed anti-slashing database, meaning that even if you were to start multiple copies of your validator client on different machines in different regions in different countries, whatever it might be, you won't get slashed. And in fact, we do this. We run many validators on the same key 24/7. We do it in CI. We do it actually, on chain, and so it works. It prevents slashing. We get little alarms whenever we might have got slashed, but it was prevented. And in our experience, that actually also helps with things like upgrades and maintenance. It makes it much easier and much less nerve-wracking. So we've also built a range of other policies. So as a couple examples, you can do things like limit the number of unstakes per day. You can require multi-factor authentication before unstaking. You can also do kind of interesting things with the deposit workflow. So for example, you can limit an ETH1 key that, say holds all the ETH you're going to stake, you can limit it to only calling the canonical deposit contract, and you can restrict the arguments to the contract. So you can say things like, well, you can only make a deposit for a validator key that I control, and also the withdrawal credentials have to match this. And so what you can basically do then is you've basically specified this is the only thing that this key is allowed to do. You've specified the correct behavior, right? So that means an attacker or an insider who gets access to the signing token, they can't take a dangerous action. They can take some action if they have your token, but those actions are only the ones that the policy allows. So the deposit policy here, for example, means even an attacker who stole your credentials still couldn't front run your validators or fund a validator that they control using your wallet, right? So you can sort of lock this down to a significant degree. And that's, to us, that's like, okay, this means that the key is doing the right thing, right? You're able to express the right thing as a policy, and then it just enforces that policy. Okay, and then finally, the last ingredient here is our virtual HSM design, which lets us kind of extend the security of a standard HSM with the much higher performance implementations of any signature scheme. So, if you've looked into HSMs on Amazon or any of the other clouds, or if you've looked into buying one, what I'm sure you know is that they only support a limited range of protocols. For anything other than AES, they tend to be dog slow. Like KMS, I think, will do 300 SecP signatures a second or something, which is just kind of ridiculously bad. And so like an HSM by itself isn't really usable, but if you seal an HSM to an enclave, now you can get kind of higher performance and the whole range of protocols that you want, and you can kind of get the best of both worlds. But of course, one decision that you have to make here is what secure hardware do you use? And we thought about this really carefully, and we ended up choosing the most boring option, which is AWS Nitro Enclaves. And to be clear, when I say boring, I mean that in a great way. Nitro, the enclaves essentially implement TPM 2.0, which is old and simple and mature and well understood. And they do it using a chip that's physically separated from the processor, which is super important. Now, frequently when we talk to people about this, we hear this question: why not just use SGX? It's like, it's so cool. And I mean, yeah, I don't know. I could go on a long rant, but it's kind of a short answer. SGX is totally broken. Intel has literally never sold a chip with a secure SGX implementation. And my bet is they never will. We have a blog post on this at cubist.dev/blog if you want to read more, but there's been attacks constantly. There was a really, really bad one at Black Hat this year. There was the SGX failed stuff last year. SGX is and always has been broken, unfortunately. So the way that we seal the enclave and the HSM, kind of getting back on track, apologies for the rant. The way that we seal the enclave and the HSM together, it guarantees that only the enclave can decrypt the secret keys. That means all other code, the operators, the root account, everyone is locked out. The only thing that can access the keys is the enclave code. And the entire system is written in safe Rust. That includes the virtual HSM, it includes the policy engine, et cetera. And all operations on secret keys, as I mentioned earlier, take place inside the secure hardware. That means generation, signing, key wrapping, and all that. Now, I mentioned easy migration, and one thing that means to us is we want you to be able to take keys that you already have and import them to the system and use them there. And so we designed this secure import process that lets you encrypt existing keys directly to the virtual HSM. You establish a connection to the HSM, it provides you with evidence that you're actually talking to the HSM, and then you encrypt to the HSM, and it now has your key and it can use it for you. And just as important, we have a procedure for securely exporting and recovering your keys. So what that means is every time CubeSigner creates or imports a key, it threshold encrypts that key to a set of hardware tokens, YubiKeys really, that you own, right? You select them when you set things up, and you say, I have these 7 YubiKeys and 4 of them are required to decrypt, or whatever numbers you want. But at least 2. So it threshold encrypts, and then it stores and immediately sends back that ciphertext to you. So the ciphertext can be stored. You can have it on hand. You can send it to a trustee, whatever makes you comfortable. And what that means then is at any time, without talking to us, you can just run the threshold decryption procedure and get your key back. And we really believe strongly that like, look, these are your keys. You should always be able to recover them, even if I get vaporized by an alien. It's your key. And you can always recover it. Okay, and then finally, I just want to make a couple comments here about like, what is the trust model? What is it? What do you have to believe to think that this whole thing is secure? Okay, so most importantly, I already mentioned this, but because of the way that the HSM and the enclave are sealed together, we can use AWS KMS key policies to permanently lock everyone but the enclave out of the secret keys. So, and in fact, yeah, it's an extremely strong guarantee that you get from the key policies. The security HSM or of the whole system relies on the correctness of the AWS KMS, which is these FIPS 140 certified HSMs, and also on the Nitro Enclave mechanism, the sealing mechanism specifically. The slashing protection database is a global DynamoDB table, so we rely on Dynamo. And our code has been audited by Veridise. We're also doing continuing audits with them, as things change. And we're also in the process of formally verifying the policy engine and Enclave code. And we kind of designed the whole thing to be formally verified, which is kind of nice. Like when you're working with an Enclave, the kinds of security properties that you have to prove are actually relatively simple. They're things like, if I the Enclave will never leak a key, and that's called an information flow control property. And it turns out that Dayon, his dissertation was on this. He's like an expert on this. So we've designed our system to be verified in that way. And it turns out also like 5 of our engineers have PhDs in things that are relevant to software verification. So they all know what they're doing. And I just get to nerd out with the crypto, which is fabulous for me. Okay, great. So to recap, look, we designed CubeSigner to make running validators at scale easier. We use secure hardware to basically give you this abstraction. It's a key that only signs the right messages, and that can protect you from all kinds of nastiness, slashing at theft, and other stuff. So with that, I'd love to take questions. Always happy to nerd out about this stuff. Please get in touch on Telegram. Yeah, like I said, would love to chat more here or elsewhere.
Thanks very much, and appreciate you kind of hitting the speed read button there in the interest of time. There was a question from YouTube, and I think it's briefly touched upon in the previous slide. What is the backend for the global slashing prevention? Is it some PostgreSDB using Web3 Signer?
Yeah, no. So we have sort of our own code here. So we're not based on Web3 Signer. We're Web3 Signer compatible, but this is all stuff that we've written and audited in Rust. And the backend is DynamoDB. So we have a global table for DynamoDB. We can, so that means, cross-region, anything that you want, you actually get sort of synchronization for the anti-slashing table.
So I think that's actually something really, really interesting to consider, not only, from a, like what this means at scale perspective, but what it also means from like a security perspective. So the slashing database is global. And when we say global, we mean across all of the users of CubeSigner, right? And not just global in the sense of all validators that a customer might be running.
So it's global in the sense that any client for your key is, essentially hits the same anti-slashing database, or the anti-slashing record. So it is, in the case that I'm trying to think. So so basically what that means is, if you're hitting the CubeSigner endpoint and making a request, then like we have a record of this is the stuff that you've signed before. This is, and we can compute if this is or isn't compatible with that slashing.
And I guess what I'm asking is, do you compute this on a per customer basis, or do you compute this globally for all validators that are in the global database? Yeah,
so that's a great question. So there's kind of 2 answers to that. So one is that the key, if you have the same key imported into like sort of multiple different instantiations of CubeSigner, those don't talk to one another kind of by design. They're sort of this independent structure. So that you should not definitely not do. But that's in some sense that's like there's something wrong with the model if you're doing that, right? Like the key should exist in one spot at all times and only one spot, hopefully, other than the cold storage export backup. So I guess what that means is like it is possible to have like 2 separate silos, 2 separate instantiations of CubeSigner, and each one has a copy of the key, in which case by design they're not talking to one another. But that's, again, that's sort of not exactly, I'd say if you want to do that, talk to us, because there's probably something weird in our mental model, and we'd love to learn more about it.
I think the recommendation is, if you want to do that, don't.
Well, that's what I would say for sure. That's the shorthand version. But the longer version is, I want to learn why, because like I'm sure there's some interesting problem that you're solving by doing that.
Yeah, it's like an XY problem. Okay. There's another question in the Zoom chat. So does the reliance on AWS Nitro enclaves essentially mean that there's like a vendor lock-in here with AWS? Or are you guys exploring other possible solutions to power the infra?
Yeah, so definitely exploring other solutions. We think this is super, super important for exactly the vendor lock-in reason that you mentioned. So there's some exciting and interesting stuff coming. So Azure has, I believe it's called TDX, which gives a very, very similar primitive, which is to say sort of, sealing an enclave to an HSM key. That's essentially the primitive that we need. Like we don't actually care that whether it runs in AWS or elsewhere. And we definitely want to get to the point where it's running everywhere simultaneously. So we definitely want to get to that point. And like I said earlier, we also want to get to bare metal. And I think the question there is just like, how do you prioritize those things? I think next public cloud is clearly the nearer term priority. But I think, yeah, all of these are possible.
Yeah, I think especially for like a lot of node operators that are keen on bare metal, the bare metal option is definitely something really, really interesting and enticing, but definitely understand that it's much easier to do this on public cloud because there's a large need for this kind of infrastructure to exist in general on the cloud side, and so it makes sense for them to develop it first. I guess another question here is, so like what happens if AWS is down? Okay, like not all of AWS globally, but at least the specific regions that perhaps are being used for the specific instantiation for a customer.
Yeah, so we can do multi-region, which means like if one region goes down, that's still okay. So the DynamoDB table is global, which means you can access it from anywhere. KMS lets you do global key replication. So those are basically the two requirements for doing global stuff. So you can already survive like, sorry, let me be clear. That means that you can survive like an entire geographical region going down. We don't have anyone running in a multi-region setup right now, but that's like definitely something that we can work with folks on if they want to do that. And in that case, what you end up with is something like a primary region and a backup region, and you basically just do that for performance reasons. I'll if I let myself go, I'll nerd out about why this is the case and why I think it's slightly annoying. But like basically, there's a little bit of like a performance advantage to knowing what your primary region is. But once you fix that, like you can have multiple other regions of backup, and then of course within a region, multiple availability zones, etc. So yeah, if a region goes down, then yeah, you can basically the idea is you fall back to another region. Now, if AWS itself goes down for a week, okay, let's put aside the fact that means that like something really, really bad had like nuclear war has happened. But like if that happens, then this is like the final safety valve is the key export. So if something goes wrong and like you just need to walk away without interacting, without contacting AWS, without anything, you can just decrypt all of your keying material and get back up and running. And so yeah, the ultimate safety valve for any kind of disaster recovery in the worst case is you just run the export recovery procedure and like you can be back up and running.
Oh, so that's pretty interesting. So you can do that without AWS actually being up, or is that dependent upon you having done backups?
Yeah, so the way that the export the recovery thing works is basically at the time that you generate the key, at that point, you immediately create the cold storage backup version of the key. And there's actually like a really interesting security reason to only do it once, which is basically like if an attacker somehow could trigger a new backup, then maybe they would get a ciphertext that you don't want them to get or something. Although even in that case, it's going to be encrypted to you, not to them. But like defense in depth is important here. So like only once at key creation time, you get this cold storage ciphertext. And then basically, we can put that in a Glacier bucket, but that doesn't help you if AWS is down, but that's fine. I mean, Glacier has never gone down globally to my knowledge. But like you also immediately get that ciphertext yourself. You can put it on a hard drive and bury it in your backyard. You can do sort of replicated whatever you want to do with it. And it's a ciphertext that's encrypted to hardware tokens, right? So like in principle, you could just like post it publicly and, unless somebody has a quantum computer that they're not telling us about, you're going to be okay. So yeah, but what the design means that you really, really don't need to interact with anyone to recover your keys. You already have all the materials. You just have to put them together.
That's super, super interesting. And is it also possible for this like let's say initial backup to be like sharded across multiple hardware keys?
Yeah, it always is. Yeah, we
Always.
require at least two, and you can decide what your sharding looks like. So so you can do like 4 of 7 or 13 of 29, or I mean, you tell me. But yeah, it's always sharded. It's always like a threshold thing. You can distribute the keys to the important people in your organization, or bury them in your backyard, or whatever you want.
Got it. Super interesting. And one last question before we wrap up from Volker in chat again. He's keen to understand how a hybrid approach, cloud in combination with bare metal might look like.
Yeah, that's a really good one. I would also love to think about how that could work. I think probably one answer is that, and this is super duper spitballing. I promise that this is happening live, so maybe I'll tell you a terrible answer. But one thing, like the thing that immediately comes to mind, like if you're going to use the cloud for something, maybe you say, look, we're going to use it for the geo-replicated anti-slashing database. So like that's the first thing that we're going to move to the cloud. That way we can have it from multiple regions, and we have sort of global synchronization of the anti-slashing information, right? And then as long as you're sure that all of your bare metal is sort of correctly interacting with that, maybe that would be a way of sort of doing a little bit of moving stuff outside the cloud. But again, that's totally a first blush answer, and I would love to think more about how different configurations give different security or performance or liveness properties.
All right, super interesting to hear about that, and I'm sure there's probably a bunch of node operators that would love to noodle on that with you.
Yeah, please hit me up on Telegram. I'm Quantum. It's there in the right corner. Yeah, would love to chat. Would love to hear ideas and yeah, learn more about how we can help.
Will do. Thank you. And maybe just one last thing, because we also talked about this a little bit in the chat while you were presenting on it. So I see the last thing on the slide here is talking about easy migration in and out. In which kind of use cases might somebody want to migrate in and out, and how does I mean, we talked a little bit about the backups, obviously, which you do in a last resort scenario, but how do you guys see people potentially moving into CubeSigner, and then when might they want to move out, and how do you guys make that process easier?
Yeah. So for moving in, there's an import procedure that it's sort of this multi-step thing. You connect to the basically you get a sort of key import key directly from the secure hardware, and you get this document there, the signature that basically proves, yeah, this was generated inside the secure hardware, and then you encrypt to that key import key and you send it back. And so that means that only the hardware can decrypt it. And so that basically the idea there is, if you're already running a whole bunch of validators, or if you've got a bunch of keys or whatever it is, you can migrate slowly to CubeSigner. Like you can, what we tend to recommend is like, migrate one, then, make sure your infra is good, and then, the setup is working, and then migrate another 10, and then migrate another 100. And so you can just sort of slowly trickle things in over time. But the idea is like, any existing setup is already compatible. You can just go through the import procedure. And by the way, we always generate that cold storage backup, even for a key that we imported, which means that you can rely on that cold storage backup, and now you have sort of one like clean, easy procedure for recovering all your keys. The ones that were imported, the ones that you generated, they all look the same. You have this cold storage backup ready to go.